On October 9, 2022, something hit Earth. It wasn't a meteorite. It wasn't space debris. It was a wave of energy so powerful that it temporarily blinded our satellites and disrupted radio communications across the entire planet. What you're about to discover is the most violent explosion ever detected in the observable universe. An event so energetic that it defies comprehension, and it happened 2.4 billion light-years away. But here's the crazy part: we're talking about an explosion that occurred halfway across the universe, and it still managed to affect us here on Earth. To put this in perspective, the most powerful nuclear weapon ever detonated, the Tsar Bomba, released about 50 megatons of energy. The asteroid impact that wiped out the dinosaurs, roughly 100 million megatons. Now, imagine an event so violent that it released more energy in just 10 hours than our sun will produce in its entire 10 billion year lifetime. We're talking about a cosmic explosion that makes every human-made weapon look like a firecracker. This wasn't just another astronomical event. This was the most energetic phenomenon ever recorded by our instruments, a blast of gamma radiation that traveled for 2.4 billion years just to reach our detectors. So what exactly was this thing? How did scientists even detect something so far away? And more importantly, what would happen if it occurred closer to us? Let's start with what scientists observed. The event has an official designation, GRB 221009A, but among astronomers, it quickly earned a nickname: the boat, the brightest of all time. On that October morning, gamma-ray detectors in space lit up simultaneously. The Fermi Gamma-Ray Space Telescope, the Swift Observatory, and multiple other instruments all registered the same thing: an unprecedented burst of gamma radiation coming from the constellation Sagitta, 2.4 billion light-years from Earth. To understand what created this cosmic monster, we need to talk about gamma-ray bursts, or GRBs. Imagine a star, not just any star, but a massive one, somewhere between 50 to 100 times more massive than our sun. For millions of years, this giant has been fighting a losing battle against its own gravity. Nuclear fusion in its core has been pushing outward, keeping the star inflated. But eventually, the fuel runs out. When that happens, the core collapses. In less than a second, material equivalent to our entire sun gets compressed into a sphere just 20 kilometers across. The outer layers of the star come crashing down, rebound off the core, and explode outward in what we call a supernova. But here's where it gets extreme. During this collapse, a black hole forms at the center, and as material spirals into this newborn black hole, something extraordinary happens to jets of energy. Moving at nearly the speed of light, blast outward from the poles of the collapsing star. These jets punch through the dying star and shoot into space, producing the most intense form of electromagnetic radiation known to physics: gamma rays. This is what we call a gamma-ray burst, and GRB 221009A was the most powerful one we've ever seen. How powerful exactly? The energy released was equivalent to converting 8 times the mass of our sun directly into pure energy using Einstein's famous E=mc equation. If you tried to replicate this with nuclear weapons, you'd need 18 quintillion of them. That's 18 followed by 18 zeros. Stack that many bombs, and the pile would stretch far beyond our solar system. Another way to think about it: if you could somehow capture all the sunlight hitting Earth for the next 300 million years and release it all at once, you'd begin to approach the energy of this single event. The gamma rays from GRB 221009A carried so much energy that they measurably affected Earth's ionosphere, the upper layer of our atmosphere. For context, this layer sits about 80 kilometers above your head right now, and a blast from 2.4 billion light-years away changed its chemistry. Now you might be wondering, how do we even detect something like this? Gamma rays are invisible, and they're coming from an incomprehensible distance away. Here's the thing: gamma rays don't reach the ground. Our atmosphere absorbs them completely, which is fortunate because they're incredibly dangerous to living tissue. This means that to study gamma-ray bursts, we need detectors in space, above the protective blanket of our atmosphere. NASA's Fermi Space Telescope was designed specifically for this purpose. It orbits Earth, constantly scanning the sky for gamma-ray events. On October 9, 2022, its detectors registered something unprecedented, a signal so intense that it actually saturated the instruments. Essentially, the event was so bright that it temporarily blinded our most sensitive gamma-ray detector. But Fermi wasn't alone. The Swift Observatory, designed to rapidly locate and study gamma-ray bursts, immediately swung into action. Within minutes, ground-based telescopes around the world were alerted. Observatories in Chile, Hawaii, and across the globe pivoted to observe the afterglow, the fading light left behind as the jets interacted with surrounding material. What's remarkable is the coordination. We built a global network of instruments, each sensitive to different types of light: gamma rays, X-rays, visible light, radio waves. When an event like this occurs, it's like an orchestra, with each instrument contributing a different piece of information. And here's what makes this detection so extraordinary. We didn't just see the gamma rays. We tracked the event across the entire electromagnetic spectrum for weeks afterward, watching as the explosion's energy cascaded through different wavelengths. We witnessed, in real time, the death cry of a star that collapsed when Earth was still dominated by single-celled organisms. Scientists built machines sensitive enough to detect whispers from the edge of the universe. And on that October morning, they didn't receive a whisper. They received a scream. So here's the question that probably crossed your mind. What if this happened closer to us? Let's run a thought experiment. Imagine GRB 221009A occurred not 2.4 billion light-years away, but just 1,000 light-years from Earth, still an enormous distance in human terms, but relatively close on a cosmic scale. And let's say those gamma-ray jets were pointed directly at us. Within seconds of the burst reaching Earth, our ozone layer would be obliterated. This isn't the gradual depletion we worry about with CFCS. This would be instant and catastrophic. Without the ozone layer, deadly ultraviolet radiation from the sun would flood the planet's surface. But that's just the beginning. The gamma rays themselves would ionize our atmosphere, triggering chemical reactions that would produce nitrogen dioxide. Our sky would turn brown. Global temperatures would plummet as sunlight got blocked. The side of Earth facing the burst would be bathed in radiation intense enough to damage DNA in every living cell. Marine ecosystems would collapse first. Phytoplankton, the base of the ocean food chain, would die en masse. On land, any organism without shelter would face lethal radiation exposure. We're talking about an extinction-level event, not the kind that wipes out one species, but the kind that resets the evolutionary clock entirely. But before you lose sleep over this, here's the reassuring part. GRB 221009A was 2.4 billion light-years away. At that distance, its gamma rays were diluted across an area trillions of times larger than Earth. What hit us was a whisper of its true power. The universe is dangerous, but it's also incredibly, protectively vast. To truly appreciate GRB 221009A, we need to see where it ranks among the universe's most energetic phenomena. At the top of the scale sits the Big Bang itself, the birth of everything. That's in a category of its own, incomparable to anything that came after. Below that, we have collisions between supermassive black holes, events that literally create ripples in the fabric of space-time itself. Ripples we've only recently learned to detect through gravitational wave observatories. And then we have GRB 221009A. This is the most energetic event we've ever directly observed with electromagnetic radiation. More energetic than any supernova. More energetic than the most powerful quasars we've measured. It stands as the brightest explosion ever recorded by human instruments. But beyond breaking records, what did we actually learn? This event confirmed decades of theoretical work about how massive stars die. It gave us data on how gamma rays propagate through intergalactic space. It provided insights into the formation of heavy elements: gold, platinum, uranium, elements that were forged in explosions just like this one. Every atom of gold in your jewelry, every bit of uranium in nuclear reactors, came from stellar deaths like GRB 21009A. There's something profound about all of this. A star died 2.4 billion years ago, long before complex life even existed on Earth, before the first animals, before the first plants, before anything more sophisticated than single cells. That star's final scream traveled through the emptiness of space for billions of years, just to reach us on a Tuesday morning in October. And we detected it, we measured it, we understood it. Carl Sagan once said we're made of star stuff. Events like GRB 21009A remind us where that star stuff comes from and just how violent and beautiful the universe's creative process really is. So yes, on October 9, 2022, Earth was hit by the most energetic cosmic event ever recorded. We survived it because the universe is as vast as it is violent. And we understood it because we're a species curious enough to build machines that can hear the universe's most distant screams. What cosmic phenomenon should we explore next? Let me know in the comments below. And if you want to see more videos like this, subscribe. Thanks for watching.